Looking at section 2.3, part 3, a strategy for graphing polynomial functions, we are going to go through the 5 steps to graph a polynomial function. We've kind of been getting our feet wet with looking at our polynomial equations. We've been looking at the leading coefficient. We've been looking at the degree of the polynomial function and determining what in general the graph is going to look like, and we've been drawing some rough sketches. As we progress, starting with today's lesson, we are going to have a lot more exact points on our graph. So we're going to get more detailed today. So we're going to go through these 5 steps to graph any polynomial function. So step number 1. It says to use the leading coefficient test to determine the graph's end behavior. So the leading coefficient test, that tells us by looking at the leading coefficient, that first number, if it's positive or negative. And then we also look at the degree of the function to determine, are they both going to the positive infinity, are they both going to negative infinity, or do we have one of each? And again, that leading coefficient kind of tells us what it looks like if it's positive or negative. Step number 2 says we're going to find the x-intercepts by setting f of x is equal to 0 and solving the resulting polynomial equation. If there's an x-intercept at r as a result of x minus r to the k power, in the complete factorization of f of x, then part A says if k is even. So if our power is even, the graph touches the x-axis at that point r and turns around. If k is odd, the graph crosses the x value or the x-axis at r. And then part C says if k is greater than 1, says the graph flattens out near r comma 0. Step number 3, we're going to find the y-intercept by computing f of 0. So that's going to give us another point on our graph. That's going to be an exact point. Step number 4 says use symmetry, if applicable, to help draw the graph. Now, some of the things we've done in prior lessons, back in chapter 1, we talked about that y-axis symmetry. If f of negative x is equal to the original function f of x, then you have that y-axis symmetry. Part B says you have origin symmetry if f of negative x is equal to the opposite of f of x. That also, reminder, it says if applicable. In some cases, you're going to definitely tell that there is no symmetry, and you might not need to do that step. Step number 5 says use the fact that the maximum number of turning points of a graph is n minus 1, where n is the degree of the polynomial function, to check whether it is drawn correctly. So remember, we look at the highest power. 1 less than that highest power is the maximum number of times that graph can turn around. So let's try an example. So we are going to look at using the 5-step strategy to graph f of x is equal to 2 times x plus 2 squared times an x minus 3. So step number 1 says to determine the end behavior. Identify the sign of a sub n, that leading coefficient. So in this case, we're going to start by looking at our leading coefficient is a positive 2. It says n the degree n of the polynomial function. So if we go and take a look at the degree, we have a second power with that first set of parentheses, and we also have what powers is with that x minus 3. Well, that's a first power, right? We don't write first powers, but we know that there's one of those things there. So altogether, this is going to be a third degree function. So it says a sub n is equal to, the leading coefficient is 2, and n, the power or the degree of our function, we said it was a third degree. So the degree 3, is that even or is that odd? Well, 3 is odd, so it's an odd function, or an odd degree. It says the leading coefficient, which we said was 2, is a positive number. So that means the graph will do what? If we have a third degree, that means we have one of each, right? One's going up and one's going down. If we have a positive leading coefficient in our case, right, that means that we have coming from the negative infinity and it's going to end up at the positive infinity. Right, just like a regular positive slope, if you had a first power, right, first degree linear equation, you would be rising from the bottom going all the way to the top. So we're going down to the left and up to the right. So the graph will rise on the right and it's going to fall on the left. Let's look at step 2. Step 2 says we're going to find the x-intercepts, or our zeros of the function, by setting f of x is equal to 0. So we're going to set f of x equal to 0. That's where the equal 0 is over here on this side. Now, when we start breaking apart our pieces, this 2 we don't really have to worry about because I could divide both sides of the equal sign by 2, and 0 divided by 2 gets rid of that 2. So all I need to worry about is each of these sets of parentheses. That means we have an x plus 2 that's squared is going to equal 0, and that x minus 3 is equal to 0. I don't really need those parentheses because those are first power. So if I were to solve, my x plus 2 to the second power is equal to 0. I can undo that second power by taking a square root, which means I'm really just focusing on x plus 2 equals 0, which means x is equal to negative 2. So our first 0 is x is equal to negative 2, and it has a 0, or sorry, x equals negative 2 is a 0 of multiplicity what? How many of those would we end up having? We would have 2 of those because we have a second power with that. If I solve my other piece, we're going to have x is equal to positive 3. Well, that's going to be of multiplicity what? Well, what power did we say was really up here? That was a first power. So in regards to those two pieces, it's good to kind of think right now, are they going to touch or are they going to cross? Remember, even is going to end up touching and odd is going to end up crossing. So if we take that 2, continued. So our x is equal to negative 2. That was a multiplicity of 2. We said that graph is going to touch the x-axis at negative 2. So that means that it's going to kind of flatten out and turn around. Our other x-intercept we said was x was going to equal 3, and that was of 0 of multiplicity 1. So that graph we said was going to cross, or crosses the x-axis at that positive 3. So if x was equal to negative 2, now remember, we are coming up from this negative here. So at negative 2, we said that the graph is going to touch and turn around. And then we have x was equal to 3. We said that that was going to cross, which if our end behavior is going to end up at that positive infinity, that means it's doing something like that. And now we're starting to get a little bit more of an idea as to what our graph is going to do, but we're not just going to call it a rough sketch and move on. We now need to take it to step number 3. Step number 3 wants us to go about computing that y-intercept. So in order to find a y-intercept, that means that we're going to plug in 0 wherever we see the x value. So that means f of 0 is equal to 2 times 0 plus 2 squared times 0 minus 3. So that means we have 2 times 0 plus 2 is 2. 2 squared gives us 4. And then 0 take away 3 is a negative 3. So 2 times 4, that's 8 times a negative 3. We end up with an x-intercept is going to be at negative 24. So that means that the graph passes through the y-axis at 0, negative 24. So again, we said, let's see, it says to help us determine how to scale the graph, we will also evaluate a couple more points. So we already said before that we were touching at negative 2, and that was going off to the negative infinity. And now we're going to cross that y-axis at negative 24. That's going to be about here. So we know that this is going to come down, and it's going to hit that point. We also know that we had that other x-intercept of 3, which means that that graph is doing something here. So now what they want us to do, because again, we're trying to make this as exact as possible, we are going to kind of evaluate what is happening in this section over in here. Because at some point, that graph has to come down and it has to do some sort of turning around before it goes back up. So we're going to evaluate 2 more points in between here to see where does that turning point occur. So that's not part of our graph yet. Okay. What we're going to do then is we are going to evaluate 2 points. We're going to evaluate 1 and 2. And why 1 and 2? Because we already know what happens at x is equal to 0. We already know what happens at x is equal to 3. So 1 and 2 naturally are just between those 2 points. So let's evaluate what those are. So kind of filling in the rest of what this says, we said that that y-intercept was at that -24. So the graph passed through our 0, -24. And it says to help us determine how to scale the graph, we will evaluate f of x at 1 and 2. So if we plug in 1, we have 2 times 1 plus 2 squared times 1 minus 3. Let's see. 1 plus 2 is 3, so 3 squared, that's going to give us 9. 9 times 2 is 18. 18 multiplied by 1 minus 3 is a -2. So that's going to give us a -36. So that means at that ordered pair, 1, -36. If we evaluate f of 2, we're going to plug in 2. So that means we take 2 plus 2 squared and 2 minus 3. 2 plus 2 is 4. 4 squared gives us 16 times 2 times 2 minus 3 is a -1. So 2 times 16, that's going to give us 32 times a -1. That gives us a -32. So that's going to give us an ordered pair over at 2. We're down at -32. So again, we'll take it back to our graph and see what we can come up with. All right. We'll do that in a moment. Step number 4 said to use possible symmetry to help draw the graph. Well, our partial graph illustrated that we have neither y-axis symmetry nor origin symmetry, right? If you went back to that partial graph, right? We did just find what happens at 1 and 2, so that's going to kind of turn back around, but you can tell by looking at that, does not have that symmetry. So it says using end behavior, intercepts, and additional points, we're going to graph the function. So to kind of save us some of that, we had already had our intercept at -2. We had our intercept at +3. We had our intercept at -24. And then those other ordered pairs that we had, we said that we had 1 and it was a -36. And we had 2 and that was a -32. So over at 1, down at -36, been somewhere about here. And over at 2, we are at -32. So if you wanted to get even more exact, you could try like 1.5 or whatever else. But at that point, that would be the only kind of estimate as to what happens within there. So it says that the degree is, we had a degree of 2 plus 1, we had a degree of 3. It says the maximum number of turning points will be 3 minus 1, which is 2. So it says because the graph has 2 turning points, we have not violated the maximum number possible, right? Turning points. We have this turning point that happened up here, and we had that turning point that happened down there. That's what they're talking about, those turning points.